Welcome to this explainer. Look, whether you're analyzing the purity of industrial mining alloys, checking the safety of municipal drinking water, or honestly, just trying to survive quantitative analytical chemistry, pinning down the exact concentration of copper in a solution is an absolutely vital skill. Today, we're bringing total clarity to this really fascinating, highly precise process. We are going to master exactly how to calculate the amount of copper 2+ ion hiding invisibly inside a solution, and we're unlocking this mystery using a classic, incredibly clever technique called iodometric titration. But here's the fundamental problem, right? How do you measure something you can't directly interact with? What happens when your target analyte, like our copper 2+ ion, just absolutely refuses to give you a clean, direct, or visible reaction with standard testing chemicals? Well, we use a brilliant mathematical workaround called indirect analysis. We don't actually measure the copper directly. Instead, we make the copper create something else, and we measure that. So, here is our lab-to-ledger roadmap for today. We're going to tackle the analytical challenge, break down the underlying redox chemistry, walk through the actual physical titration procedure, and finally, calculate that exact copper concentration.
All right, let's jump straight into part 1, the analytical challenge.
The technique we're relying on here is called iodometry. It is honestly the perfect indirect method for when your analyte, again, copper 2+ in our case, is a strong oxidizing agent but doesn't give a clear measurable endpoint on its own. So instead of fighting the copper, we're actually going to use it to liberate a very specific, highly proportional amount of free iodine.
I want you to think of this like the ultimate chemical transaction. Iodine is basically our temporary currency, a stoichiometric middleman. It elegantly bridges the gap between our unknown copper concentration and our known titrant, which is sodium thiosulfate. The copper essentially buys the iodine from a chemical reserve, dumping it right into the solution. And then we use the thiosulfate to pay for it, neutralizing the iodine. If you track the payment, you know exactly what the copper bought. Which brings us to part 2, the redox chemistry. Let's look at the first crucial reaction here. Our unknown oxidizing agent, the copper 2+ in our flask, is hit with a massive, unmeasured excess of iodide ions, usually from potassium iodide. The copper reacts, it precipitates out as a solid called copper iodide, and, here's the important part, it liberates free molecular iodine straight into the solution. Next, we take that newly liberated iodine, our middleman, and we titrate it. We systematically drop a standard reducing agent, sodium thiosulfate, from our burette. This thiosulfate reduces the free iodine right back down into invisible iodide ions, while the thiosulfate itself gets oxidized to tetrathionate. Now check out this quote from our source material. Pay close attention to the word equivalent. Since we totally flooded that initial solution with excess iodide, the exact amount of iodine liberated flawlessly mirrors the original amount of copper. The copper completely dictated how much iodine was released. And you know, this equivalent relationship, that's the magic key that makes the entire calculation possible. Okay, moving right along to part 3, the titration procedure. Let's look at the lab protocol. But wait, before we even touch a flask, the environment has to be perfect. The solution's pH absolutely must be maintained between 4 and 5.5. If it's too acidic, the air actually oxidizes our excess iodide, creating extra iodine and totally ruining the results. Too basic, the iodine reacts with hydroxide ions. This strict pH window is basically our ultimate guarantee against nasty side reactions. So here is the step-by-step recipe. We kick things off by adding that huge excess of potassium iodide. Then we immediately start titrating with our standard thiosulfate. Now hold off on the starch indicator until the color naturally fades. Then you add it, along with a special compound called thiocyanate, and carefully titrate drop by drop to the very end. I gotta say, the true beauty of this specific titration is the vivid visual cues it gives you. When the iodine is first liberated, boom, the solution turns a deep brown. As you add the thiosulfate, it gradually fades to a pale straw yellow. That is your cue to add the starch indicator, which binds to the remaining iodine and turns an intense dark blue. You just keep titrating until that blue entirely vanishes, leaving a really distinct pale pink solid precipitate. Actually, there is a pro tip here that separates a decent analysis from a perfect one. It's step 4, adding about 1 gram of thiocyanate right before that final endpoint. Why do we do this? Well, the solid copper iodide precipitate actually traps or absorbs some of the free iodine right on its surface where the thiosulfate can't quite reach it. The thiocyanate brilliantly kicks that trapped iodine back out into the liquid, making absolutely sure we count every single molecule. Finally, part 4, calculating copper concentration. Time to bridge the lab to the ledger. Let's look at the stoichiometry we just pulled off. If we compare our two chemical reactions side by side, we can clearly see that 2 moles of copper react to liberate exactly 1 mole of molecular iodine. Then, in the second step, that exact same single mole of iodine requires exactly 2 moles of thiosulfate to be completely reduced. Since both the copper and the thiosulfate are mathematically tied to that exact same mole of iodine, we can just cancel out our iodine middleman entirely. And when we do that, the complex chemistry simplifies so beautifully. 2 moles of copper equal 2 moles of thiosulfate. And obviously, a 2-to-2 ratio simplifies straight down to a perfect 1-to-1 molar ratio. Just look at how incredibly clean that is. 1 mole of copper 2+ equals 1 mole of thiosulfate. It makes calculating the amount of Cu2+ straightforward. The exact number of moles of thiosulfate you dispensed, which you easily know from the volume and concentration in your burette, is it literally exactly equal to the moles of copper 2+ that were hiding unseen in your flask. Divide that by your original sample volume, and you've got your exact copper concentration. As we wrap up this explainer, I really want you to think about this. How do indirect measurements shape our understanding of the unseen world? This iodometric titration of copper is way more than just a cool lab trick. It's a total masterclass in scientific problem solving. By understanding the chemical middleman, we can bypass direct roadblocks and use the rigorous laws of stoichiometry to pinpoint the invisible elements that shape our universe. Thanks for hanging out with me today.